Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today's session, which is supposed to be our tutorial number 5, we like to solve problems from handout number 5, which is regarding Gauss law. Okay, from our previous discussion, we have done example of number 3, okay, and for today session, inshallah, I'm going to try to solve problem number 2. As you will see later on, the structure is exactly the same as in problem number 3, but the only difference is the type of charge that we are dealing, and by that you can see the solution will be totally different compared to our previous problem, but yet the method that I'm going to use is repetitive. It's exactly the same. So let's do it now. Okay, so let's do problem number 2 of your handout number 5. A thin spherical shell, so we still have a shell structure in a sphere shape. Radius A carries a uniform surface charge density rho s, but now the structure is not carrying a volume charge, it's carrying a surface charge. So determine the electric field intensity in all regions. So what we have is a sphere, a thin sphere, okay, so that should be our thin sphere with radius given as A, but the only difference compared to the previous example, now we are dealing with surface charge rho s. Okay, that's the only difference. So now we are dealing with surface charge rho s, and we need to do what here? We want to find the field in all regions. Okay, so I'm going to use Gauss law to solve this problem. From this structure, I can see clearly there's going to be two distinct regions. One region is inside the shell. I'm going to denote as region number 1. Another region is outside the shell. I'm going to denote as region number 2. Okay? So that's to be two distinct regions that can be extracted from our diagram. So I'm going to solve for region number 1 first. Okay, region number 1. So what we did before, we clearly defined a position in region number 1 where you want to find the electric field density. That should be our representation of the general position of region number 1. Then what I have to do, I have to build a Gaussian structure. Should be passing through this point of interest, and second characteristic should be completely closed. So I'm going to define that to be another sphere. But the radius now is given as r because the point here is not fixed. So R to show generality, meaning that this point can move within region number 1. So therefore, to define that clearly, R should be defined as smaller or equal to A. So therefore, that should be the definition of region number 1 based on our diagram. Okay, that should be step number 2. Again, I'm repeating the process of Gauss law. Step number 1, we define clearly where is the position of our D field. Step number 2, we're going to build our Gaussian. Should be first passing through the point of D, second should be completely closed. So due to the shape of the problem, I'm going to choose my Gaussian to be similar, which also a sphere. Then step number 3, I'm going to define the mathematical Gauss law. We state d dot ds must be equal to q enclosed. Okay, that should be step number 3. Okay, so how we proceed? So we're going to link this equation to the shape of the Gaussian, and from our experience, that should be denoted as dr 4 pi r squared, correct? Because the r, this r is defined as this position in the diagram. And let's say, what should be the charge enclosed by the Gaussian? Is there any charge located inside this Gaussian? From the diagram, what we can see, the charge is actually residing on this particular surface, which is now, from the diagram, is located outside our Gaussian shell. Therefore, we can't see any charge inside this Gaussian. Due to that reason, we're going to say that the Q enclosed will be equal to 0. And from here, we're going to say that the region number 1 will be equal to 0. And finally, we know that E equal to D divided with epsilon naught, assuming the medium is free space. So E number 1 will also be equal to 0. Okay, that should be our electric field intensity in region number 1. So let's do for region number 2 now. We're going to repeat again the same process. Region number 2. Okay. So for region number 2, location wise, yes, should be here. Then I'm going to draw my Gaussian. Should be this structure located on region number 2, and then the radius should be given as r. Now my r is greater than a. So now that should be the range of region number 2. So the solution we obtained in region number 1 cannot be used to represent the field in region number 2. Similarly, later on, the solution we obtained for region number 2 cannot be used to represent the field in region number 1. Okay, so let's repeat the process now. Mathematics, d dot ds equal to q enclosed. But remember, now we are referring to the blue sphere shape, not red or not black, the blue one. That should be our structure that we refer for region number 2. And again, due to the nature of the shape, we know the left hand side will end with dr 4 pi r squared. But now we can see there's a charge residing inside this Gaussian profile, which is the surface charge. And then for the surface charge, we know that should be rho s dsy, because that is a standard model representing surface charge. So now what should be our ds? And our ds, based on the shape of our sample here, we know should be a squared sine theta d theta d phi. Okay, that should be. And now when we solve the mathematics, on the right hand side will end with rho s 4 pi a squared. And for region number 2, the d2 will be equal to rho s a squared divided with r squared in which direction? Yes, r direction. Okay, because we can cancel the 4 pi. And for E number 2, which is requested by the question, the question asks us to find electric field intensity, not electric field density. So you must find the E should be equal to rho s a squared over epsilon naught r squared in r directions. Okay, that should be our E2. Okay, so now you can see there's no field in region number 1, but they're going to be field emitted by the charge in region number 2. Okay, so that is Gauss law that you can use to solve this type of problem. But shall we do another problem? Or you think it's enough? Okay, let's do one more problem. Okay, one more problem. Okay, from the same handout. So let's do slightly different shape. Okay, let's do problem number 11. Okay, you read the problem first. So you need time to read the problem. So okay, what the problem said, number 11, from the same handout of Gauss law, a uniform volume charge. So now we have volume charge, and then we can see clearly the symbol representing the volume charge is rho v, and then Coulomb per meter cube. But the volume charge is not constant because we can see variable r inside the definition of volume charge density lies within the cylinder r equal to 1. And rho v equal to 0 as well. So meaning that this rho v only exists inside the cylinder within the range r less than 1. Yeah? For other region and other range, other position, meaning that above than r equal to 1, is not, there's no charge. Find d everywhere. So let's focus on this one first. Find d everywhere. Okay, problem number 11, handout number 5. Okay, so let's draw it first. I'm going to draw my cylinder. Since I want to use Gauss law, that's what my intention. For Gauss law, I mean, condition that allow Gauss law to be used is very specific, and one of the criteria that we can use Gauss law when we dealing with infinitely long line structure. Okay, so now we have a cylinder, and then we want to use Gauss law, and not mention in the question actually the actual length of our problem of our cylinder. So therefore, in order for us to use Gauss law, we must justify why we can use Gauss law. So to do that, I'm going to assume, okay, cylinder infinite. Okay, that's what must be clearly stated. Without that assumption, I cannot use Gauss law, because Gauss law can only be used for certain condition of charge distribution, and infinitely long line charge is one of the criteria that allow us to adopt Gauss law as a method to solve this problem. So therefore, I'm going to define clearly is infinite by drawing this dotted line. Okay, so just make it part of it. So this is our cylinder. Okay, so that should be clearly shown in order for us to adopt Gauss law. And then the radius having r equal to 1, so I'm going to give this r equal to 1. Okay, 1 meter. So, and then what given here is the volume charge, rho v, equal to 60 R Coulomb per meter cube. So this rho v only reside inside this cylinder. There's no rho v outside. So find D everywhere. Okay, what should be our next step? Good. The typical question we always ask in EMT, what coordinate system we should use? The answer should be cylinder. So that should be my second step I'm going to determine. Cylindrical coordinate. Okay? Then how to make it simple? I'm going to assume that the axis of this cylinder is coinciding with what? Good, z-axis. Okay, that should be the logical thing I'm going to do. So therefore, the z-axis coinciding with my cylinder. Okay, so now I'm going to use Gauss law to find D, and from this diagram I can see there's two distinct regions appear to be clearly seen. First, I can see one region is inside the cylinder. The second region is the one located outside the cylinder. Okay, that should be my third step, defining regions. That must be done based on our diagram. Okay, I can see there's two distinct regions. One is inside the cylinder, so I'm going to define that to be my region number 1. Another region is outside the cylinder, therefore I'm going to define it to be my region number 2. So now I'm going to start solving my Gauss law by doing first region 1. Okay. So, where's my region 1? Okay, I'm going to make my region to be here. Okay, this is my region number 1. You can see it's inside this particular region, so therefore this representing my region number 1. If I'm drawing the cross to be here, that should be presenting my region number 2. So now I'm going to build my Gaussian profile. So the Gaussian profile first must be the surface must pass through the point where you want to find the D. So that should be our point, must pass through the point. Second, must be completely closed. Okay, so in order to make it easy, and we already adopt cylindrical as our coordinate system, So I'm going to make my Gaussian profile to have a cylindrical shape structure. Okay, so what I mean by that, I'm going to build a cylinder where first the surface passing through the point D, and the second must be completely closed. So that should be my Gaussian profile structure for this problem. Okay. And then since the dimension must be defined, and you can see it's not infinite now, the dimension is finite, I'm going to set the height of my Gaussian cylinder should be h, and then the radius should be what now? Because the point is moving, therefore the radius must be variable, must be r. So now the r must be clearly defined to be smaller than 1. Okay, that should be defined. Okay, so that's done. So let's go to the next step. We need to solve the mathematics now. D dot ds equal to q enclosed. So let's solve the left hand side first. I'm going to make it to be left hand side, and then this to be right hand side, just to make it not to muddle up. So meaning that I don't have to cram everything. I just want to make nice. So I'm going to solve for the left hand side part now. So should be equal to 1. So I can see there are 3 distinct surfaces of my Gaussian profile. What I mean by that, I can see I can split this structure into 3 different surfaces. I'm going to denote this to be surface number 1. This part of the surface of my cylinder to be surface number 2. And the surface that I can see at the bottom of the cylinder going to be surface number 3. Okay? So I'm going to split that mathematically. What I'm saying to myself, okay, should be surface 1, d dot ds1. That refer to this particular surface. I'm going to add with surface number 2, d dot ds2. Okay, that refer to the curved surface of the cylinder. And finally, surface number 3, the bottom surface of the cylinder, d dot ds3. Okay, so now we have to substitute the symbol of this equation with the information extracted from our diagram. Okay, what should be my ds1 here based on the diagram? Anyone can know here? Okay, ds1 is the one on top here, the sample position. Therefore, should be what now? Should be r dr d phi in z direction. Agreed? Okay, for surface number 2, what should be my ds? Okay, change of phi, and what else? Change of height should be r d phi d z. Okay, which direction? R directions. And surface number 3 is quite similar to surface number 1, so the magnitude should be the same. R d phi dr. Okay, in which direction? Minus z direction, because direction is showing upward of the Gaussian profile. So showing upward, so positive z, outward, positive r, outward meaning down in this direction should be negative z. So that's done. So the ds must be substituted based on our table handout 2, referred to our Gaussian profile structure. Okay, now how about the d? the d must come from the nature of our source, because from our Coulomb's law example that we did regarding infinite line charge, remember when we have the rho L to be infinitely long, the field must always be normal to the source. And then due to the nature where the charge is aligned the z-axis, the only component of field appear in our solution is only R component. Okay, I hope you can recall that. So therefore, I'm going to use that analogy here. My D will only consist of the R component. So that is important. So this is the reason why this result behaving as such, because we assume the structure infinitely long, therefore the D have special behavior which is only in the R direction. This conclusion comes from our experience solving infinite line charge problem in Coulomb's law when we deal with Coulomb's law theorem before. Similarly, D here, the same, I'm going to make it to be dr in R directions, and here also dr in R direction, because we are dealing with the same type of source. Okay, so let's do the mathematics now. R dot Z will give us what? It's dot product, remember? So therefore, this term will end with 0. Dot product. R dot R will give us, yes, 1. And R dot negative Z will give us 0. So we only end with the second surface. And when we solve the mathematics for the second surface, it's going to be equal to, okay, integration of dr, and then should be R d phi dz. So double integration, the limit must refer to the Gaussian structure. What should be the phi? Complete circle to pi. What about the z? Yes, from 0 to h. Because we define the height of our Gaussian cylinder to be h. So my left-hand side solution will end with a dr multiplied with 2 pi r h. Okay, that for the left-hand side. Now let's do the right-hand side now. Right-hand side. Okay, what is the charge residing inside this Gaussian? The answer, yes, is a volume charge. Therefore, when we have a volume charge model, the mathematics representing that sample must be rho v dv. Okay, and then have to substitute properly now. For rho v is not constant. 60 multiplied with r, that should be our rho v. How about the dv? Okay, you can refer to your handout too. Should be r dr d phi d dz. So how many integration that we have to deal now? Triple integration. What should be the R range? Remember, the charge that we must consider here is the Q enclosed inside this Gaussian. For the R must be from 0 up to R. The phi 0 up to 2 pi, and the Z 0 up to H. Okay, so therefore what you're going to have now, 60 integration of R squared dr, integration of d phi, integration of dz. 0 to r, 0 to 2 pi, 0 to h. Okay, and then the right hand side that we're going to have here will be equal to r cubed over 3, so 20 r cubed multiply with 2 pi multiply with h. So our final solution going to be 40 pi r cubed h. So what we want to determine actually the field. The question asks us find the electric field density everywhere. So we want to find the D. What should be the D? Yeah? So therefore we have to equate them. So meaning the left hand side is equal to the right hand side. Left hand side is what? This term. So finally, what we have, dr 2 pi rh is equal to 40 pi r cubed h, and we're going to end of D region number 1 as equal to 20 r square. In which directions? R directions. So that should be the solution for our D in region 1. Okay. All clear? Okay, so let's do for region 2. Just to show when you see the logic behind it is going to be a repetitive step. Okay, region number 2 now. That my concern, region number 2. So again, I'm going to build my Gaussian. So this is the location where I want to find my H. So my Gaussian going to be another cylinder. Okay, that should be my Gaussian. And then you can see the radius here is R. So therefore I'm going to define my region number 2. R is greater than 1. You can see I purposely choose red ink marker here so that you can see I'm referring the Gaussian profile drawn with the red ink, okay, which is residing outside my cylinder, my charged cylinder. Okay, so let's continue repetitive now. D dot ds equal to Q enclosed. Okay, so I'm not going to repeat the same process. I'm going to use my experience now in order to find my solution. So based on my experience, on the left hand side, we end with this particular result. So I'm going to say left hand side dr 2 pi rh, because I'm assuming the height still h here. Okay, so therefore my solution is going to be 2 pi rh equal to, so I'm going to say now my volume charge now. My volume charge here, you can see is only inside cylinder R smaller than 1. For region R greater than 1, there's no volume charge. This argument is clearly stated by the question, because the question said that the volume charge density only exists within the cylinder of radius R equal to 1. Okay, therefore, outside the region R greater than 1, okay, outside the region R is greater than 1, there's no volume charge, so meaning that the limit of my integration for charge later on only from 0 up to 1. Yeah? So that's what the consequence of it. So I'm going to use this mathematics, but the only difference here, the limit now 0 to 1. So I'm going to say 60 integration from 0 to 1. Okay, and then R square dr, and then this should be dq, this should be dz. Okay, so it's going to end with same mathematics before, which is 40 pi h, because R equal to 1, because that should be the range of our limit R. And D2 should be equal to, okay, so I'm going to solve the mathematics so the pi can be cancelled out, should be 20. What else? Can I cancel the R? No, so divide with R. Which direction? R directions. So that should be our solution. Okay, so you can see by assuming again the structure to be infinitely long, then only we can assume we can solve this problem using Coulomb's law. And by using Coulomb's law, the steps taken is consistent, whereby the first thing I'm going to assume which charge, then I'm going to define the appropriate region based on the structure given by the problem, whereby in these examples there are two distinct regions, so I denote as region 1, region 2. Then going to place a position in that particular region and build the appropriate Gaussian profile. Then going to solve the Gauss law equation with respect to the built Gaussian profile, and then everything come back to the mathematics and the tools of handout number 2, which are the table, which is the table 1, the table that we built in handout number 2. Okay, so I think I have completed doing some examples, but I know you need to do more examples to make yourself more aware about the nitty-gritty of Gauss law. So if any one of you got problem regarding Gauss law, especially question that you don't understand, you can email to me, so it's easier for me to which problem you don't understand, and I try to help you by answering your query, rather than me giving general solution whereby it look easy and simple. Actually, it's easy than simple, inshallah. Yeah? So thank you very much. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.